Hi guys, in this video we're going to talk about random variables. We're going to start by defining them. So a random variable is a little bit different than a concept of just a plain old variable that you may have already learned. So a random variable, and you'll often see in these slides I may abbreviate with RV. It's a numerical variable whose value depends on the outcome of a chance experiment. Remember, we're in the context of probability right now, and we're dealing with chance experiments, which are any situation where there are two or more possible outcomes and we don't know which one is going to occur. There's uncertainty as to which of two or more possible outcomes will occur. So in that case, we can define a random variable as a numerical variable whose value depends on the outcome of that chance experiment. Another way you could think of it is it's a random variable associates a numerical value with each possible outcome of a chance experiment. And a slightly more technical definition of a random variable is a real valued function defined on the sample space. And you recall from previous probability lectures and tutorials that a sample space is a collection of all possible outcomes of a chance experiment. So if you define a function on that sample space, you have created what's called a random variable. And just to be clear, a real valued function. Okay, a little bit about notation, although most introductory textbooks don't do a lot to distinguish capitals and lower cases, but when you're dealing with random variables in more intermediate and advanced probability texts, you will notice, and so I mentioned this, that the random variables are capitalized, and we tend to use letters from late in the alphabet, okay? And you'll also see lowercase letters, Roman letters like X, Y, and Z, and U, V, T if you need more. The distinction is that the capital is the random variable, the lowercase is a particular value of that random variable. Okay, and you may see that throughout my slides. I don't make a terrible stink of it, but I did want to mention this, especially for those of you who are planning to move on, if not simultaneously taking a probability course. Okay. All right. So I'm going to split the rest of this lecture up into discrete random variables and then continuous random variables. So discrete random variables. Let's give a little definition, or a little overview rather. Probability distribution of a discrete random variable, say X, gives the probability associated with each possible X value. This is called a probability mass function, abbreviated PMF. A PMF can be displayed either in a table or an equation and even in a graph. But usually you'll see it either in a table or an equation. Okay? You'll see an example of a table directly below here. And so here we have a little example going, and although there's no background to this example, I could throw in a little bit of background for you. Let's define X to be the number of car accidents for a male aged 30 to 35 in a given calendar year. So let's say 2020. You can either have, according to this PMF, which in this case is in the form of a table, go back to the definition of a PMF, the possible values of X are 0, 1, 2, and 3. This is clearly discrete, right? You can have 0, 1, 2, or 3 accidents. You cannot have anything in between these. Okay, so this is not continuous, it's discrete. There is a finite, in this case, finite number of possibilities. And remember, discrete can also be countably infinite as well. It's when you get into uncountable infinities where you have to deal with continuous random variables, things like time, but we'll get there shortly. So we're clearly dealing with a discrete random variable. That's the first thing we should recognize, and the possible values are based on present evidence given to us here as 0, 1, 2, and 3. Then to complete this and really make this a probability mass function, we have another row here which gives us the probability of each of these possibilities. Okay, so this row is labeled the probability of x equaling a particular value. Notice the lowercase uppercase distinction. Another notation which is equivalent for discrete random variables is this notation, because there is a, what we say, a mass at every possible value. So we can also just write this in this form or this form. Okay, so the probability, what this tells me here is that the probability that x equals 0, meaning no accidents, is 70%. Probability that x equals 1 is 22%, or 0.22. The probability that x equals 2 is 0.05 and x equals 3 is 0.03. These must all add up to 1 or 100%. So you should always check this, or else this is not a probability mass function. Okay, so let's do a couple examples. These may seem very easy, but there's an important lesson here. First question, what's the probability that x equals 1? You just take that right off the chart, right? What's the probability that x is greater than 1? So let's think of that. It can't include 1, but it include everything greater than 1. So we're talking about 2 and 3. So we add up these probabilities. So 0.08, right? And let me just, for this one, point. Okay. What's the probability? And here, these seem very simple, but I'm making an important point here. What's the probability that x is greater than or equal to 1? So this includes 1, so we need to include 1 here. This may seem very trivial to you, but pay attention. I'm going to tell you this is not going to be the case when we deal with continuous random variables. Okay? So here the answer would be 0.3 or 30%. Okay? Now, this is an important point. When you're dealing with discrete random variables, there is a distinction between greater than, equal to, less than, or equal to, and you need to pay attention to that. Okay? Moving along, some properties of discrete probability distributions, like the one that we just saw here and expressed in the table. For every possible x value, the probability must be between 0 and 1 inclusive. Probability of 0 means that outcome will never happen, or that value rather will never happen. Probability of 1 means that value is certain to happen. Usually we're dealing in practical cases with something in between these two. Okay? The other property here is that the sum of all x's such that the probability of x is greater than 0, which just means for the sum of all x's where there is an actual possibility of occurrence. All possible x values is another way to think of it. Okay? For the probability of all these x's is equal to 1. So one more time. The sum of all the probabilities for all x values that are possible must equal 1. These are two properties we can very quickly check. First one, all between 0 and 1. Second one, these all sum to 1. You could check that if you haven't already. Great. Moving along. We can talk about the mean or expected value of a random variable. So for discrete random variables, the mean is defined as such. Okay? The notation, you will often see this in some textbooks or this in others. These are alternative notations and both have their merits. So I just use both. So this is alternative notation for the mean or expected value, synonymous in this case, of a discrete random variable. The definition here, again, is if you were to take each possible value and multiply it by its probability, you will get the mean or expected value. So question 4, pause this video and check or try to get the mean of the in the example that we had before. Okay, so what you would do here is you would take 0 times 0.7, 1 times 0.22, 2 times 0.05, and 3 times 0.03. Add these up. That's what the definition of expected value is. And if you do this, you will get 0.41 or 0.41. So the expected value of x, or the mean of the random variable x, equals 0.41. Okay? One last note on the mean or expected value. This, especially this notation and this term, may remind you of concepts from statistics. The mean, right? And you'll even remember this notation, mu. Well, I want you for now to put those two things aside and just approach what you're doing now as a probability topic, and don't conflate it just yet with somewhere else where you've seen this, which was in descriptive statistics. These two concepts are very similar. Probability takes a different approach. It talks about the possibilities of things occurring, whereas in statistics, we look at it from the other perspective. That is, things have occurred, we've collected data on them, and now we're reflecting on the data and computing things based on present evidence. Two different perspectives, pre and post. Okay? These two concepts will converge when we get to inference, but for now, just maybe keep them separate in your head, or you could start thinking about the way I described it. Now, moving along, we can also talk about the variance and standard deviation of a random variable. And for a discrete random variable, the variance is defined as such. Okay? So what you're going to do is you're going to take every possible value of x, subtract its mean, so you've computed the mean prior to coming to compute the variance. You're going to square that difference, then you're going to multiply that by the probability of that particular value of x. Then you're going to sum them all up after you've gotten them all. Okay? Again, notationally, you'll see we have the sigma notation, which should be familiar to you, or this alternative notation, both of which are useful, and you'll see this one in more advanced texts, and they both have their merits. Okay, so let's go back and compute the variance of x from that example we were working. Okay, so we know the mean was 0.41. So what we're going to do is first start with the first possible value of x, which is 0. Subtract 0.41, square that difference, then multiply by its probability. Okay, and that's the first element. Plus, then we go to 1. 1 minus 0.41, which was the mean, squared, times its probability. And then do that for 2 and 3, and once you've, so I'll just do ellipses here. Once you've completed all that, you should get 0.5219. Remember, this was number of accidents, so you could say number of accidents, and the appropriate unit here is squared. Okay? So there's the variance. Now, if we want the standard deviation of this, just like you've learned in statistics, the standard deviation is just the square root of the variance, so you can easily compute that. Okay? So that is how you compute the mean and the variance of a discrete random variable. And there's a little overview of these and how to interpret them. The mean or expected value is the long run average of the results from this chance experiment. So let's think of it this way. You run the chance experiment over and over and over and over, millions and millions of times if you have to. And then you take the average of all those, this large number of times that you've repeated the chance experiment. And so for us, you'd get zeros, ones, twos, and threes. You get a lot more zeros you'd expect than threes, and ones than twos, etc. And if you were to average all them, that would be the mean or expected value. Okay? The variance, you can think of this as a measure of the variability or uncertainty of the outcome of a particular random variable, a chance experiment, and as a result of the random variable. Okay? So the higher the variance is, the more you could think of that as a measure of more uncertainty of that random variable, of the outcome of that random variable. The lowest variance and standard deviation can be are 0. You can never have a negative variance or standard deviation. The lowest it could be is 0, and that would only occur if the chance experiment was not really a chance experiment. Think about it. There was certainty as to the outcome, so there was no variability. Otherwise, you're going to have some variability. Okay? Now, moving along now to discrete random variables, and here we're not going to be able to do much as far as like physical or applied examples, but we're going to learn about this more conceptually, and I'll tell you why we have a limitation here. So let me just read through some of these important bullets. Probability distribution of a continuous random variable is specified by a curve called a probability density function, PDF. It's a function, so you could say f of x, the function that satisfies the following two properties. So this function must satisfy these two properties, and you'll notice that they're very similar to the two properties that the discrete probability distribution needed to satisfy. First, the function must be greater than or equal to 0. That is, this function, this PDF, can't go below the horizontal axis. 2, the total area under the PDF must equal to 1. That sounds very interesting. We learned a little bit about area under histograms being equal to the proportion in a given range of values. Now here we're in probability, and we're hearing again now this idea of a curve, and you could glance down here and see some of these PDFs examples, and you see the area in purple there shaded, and you see okay, so that area is equal to the probability, and so the total area under the curve must equal 1. Interesting. Remember, in the histogram, the total area under the histogram must also equal 1. We're talking about density histograms, and notice the word density comes up here as well. So hopefully you're starting to make some connections slowly. You don't need to force it. Just learn this as a pure probability introduction, and then later reflect when you review some of the earlier stat lessons that you've learned about density functions, about numerical summaries of data like the mean and the variance, and maybe you can start making some connections between the two. Okay, so there are the two properties, and I did mention something without actually going through it, defining it, or at least reading this definition. The area under this function, this so-called PDF, is in a particular interval is equivalent to the probability of getting a value in that same interval. So if someone were to ask you, let me jump to this picture. If someone were to ask you, hey, what's the probability that this random variable x, by the way, it's continuous, what's the probability that it's between this constant a and this other constant b? Let's just give some numbers, 5 and 7. What's the probability? What you would literally have to do is take the PDF, graph it, and then find 5 and 7, or A and B, and shade the area between those two and find out what that is. Whatever this area is equal to the probability of that range. Okay? I want you to understand this conceptually, because finding this area turns out it's quite difficult and tedious to do, and for an introductory or intermediate stat course, you may not be asked to do this. I will not do this in this particular lecture and this course. So what you can do is I want you to do is focus on the concept here. And here is a picture of the total area under the curve, all the way from the lowest possible value to the highest possible value. This must equal 1. So in other words, you're saying, hey, what's the probability that something's going to happen between the minimum and the maximum? Obviously 1, right? Okay. Another thing I want to mention here before I move on is that in the continuous case, there is no difference between less than or equal to, greater than or equal to. There was a difference in discrete random variables. The difference here is that there is no area at any particular point. There is only area once you look at an interval. Okay? So there we will never, in continuous probability, in continuous random variables, you'll never be asked a question. Well, you shouldn't, unless it's just to test your knowledge, that x equals, let's say, a being just a real valued constant. The answer to this would be 0. Okay? And so there's no difference between these guys. All right? In the discrete case, we say there is a mass at every possible point. That is not the case in the continuous random variables. Okay? So moving along, mean and expected value, variance, standard deviation of a continuous random variable. We're not going to learn how to compute this because this requires some background in calculus, at least a couple semesters, if not more. You need calculus, but it's important to understand that these same concepts exist for continuous as they did for discrete random variables, and they have the same interpretations. This is important. Rest assured, we will deal with a few continuous random variables, okay, and their distributions this semester. And for each of these, we will have a table of values associated with that table to help us answer questions of probability. So what am I saying here? If I ever were to ask you, hey, what's the probability of a continuous random variable, let's say x or y, let's stop using x so you don't get too attached to x. Y is continuous, and by the way, here's the PDF of y. By the way, the y-axis is density. You can write that out. And I say, what's the probability that y is rather between a and b here? Okay, so you'd have to give me this area. Well, you didn't take 3 semesters of calculus. And by the way, this function is going to be very ugly to begin with. It's not going to be easy to integrate to begin with if you did take any calculus. So for our case, if you ever have to answer this kind of question, there will be a table that you will be able to go to get this area. So we're only going to deal with a few of these continuous random variables and their probability distributions, and namely the ones that we have tables for: the normal distribution, the t-distribution, the chi-square distribution, and maybe the f distribution. Okay? Other than that, we would need to have that background in a few semesters of calculus, but I want you to still understand the concept generally, and you will actually get a chance to compute some of these areas with the help of the tables later down the line. Okay? And then I want to just end off with talking about linear functions of random variables. So sometimes we're not interested in the random variable itself per se, but we might be interested in some function of that random variable. So here's some properties of expected value and variance that I want to get out there and that you can kind of add to your little cheat sheet or your study sheet. Let a and b be just, again, real valued constants, and we want to investigate the random variable y. And y turns out is equal to ax plus b. Well, if this form right here that you're seeing, this is a very specific type of function. This is called a linear function, okay? And a and b are, like I said, real valued constants. So if you have a function like this, it's linear. And if that function is of a random variable and you're interested in now finding the mean, expected value, variance of this new random variable that you created by taking a linear function of this other one, x, then you don't have to do a lot of work like you did originally when we computed it in that previous example. It turns out there's some interesting results, and here are the results without proofs. So the expected value of y, you can rewrite that as the expected value of y, what y equals, right? And that is going to be equal to, and here's the result, a times the expected value of x plus b. Okay, so take note of this. Okay, likewise, the variance of y, you can rewrite it as the variance of what y equals to, which is ax plus b, this linear function. That's going to equal to the part that you're multiplying x by squared times the variance of x. So b has no impact. In other words, what you add and subtract to a random variable does not affect its variability. It just shifts all the numbers one way or another depending on the sign. But what you multiply the random variable by will affect the variability. It could make it more variable or less variable. Okay? So that's why you don't see b in this final result here having any impact. Okay? And let's do an example and finally kind of wrap this all up where we take a linear function using the previous example. So let's say that we're an insurance company and we have a way of coming up with your annual payment or maybe monthly payment, whatever it is. Let's say we charge you a fixed amount of $500 plus $300 for each accident that you have at the end of the year. Okay? So let's think about this. So the number of accidents has an impact on how much you get charged. But even still, you're going to have to pay $500 even if you don't have an accident. So if you recall in our example that we worked earlier, here x was the number of accidents. So this is building on this example. So the possibilities were 0, 1, 2, and 3. So coming back here, I can get, if I do 500, right, dollars plus $300 times the number of accidents, which if you recall, we called x. X could be 0, x could be 1, 2, or 3. This will give me how much you're going to pay at the end of the year. Let me just call that y to distinguish it from x. Okay? So here, look, it looks like we have a linear function of a random variable, namely x. And if we keep with the a and b that we used before, this is ax plus b. Now don't be thrown by the order of these. We're adding here. So ax plus b, you could write 300x plus 500 if it makes you feel better, equals y. We are dealing with a linear function. And so when question 6 asks us what is the mean amount charged, we're not asking the mean number of accidents. Y now is the amount charged. So we want the mean of the random variable y. If you have no accidents, you're going to plug in 0 here. You're going to pay $500. If you have one accident, you're going to plug 1 in here. You're going to pay $800. If you have 2, you're going to pay $600 plus $500. So you're going to pay $1,100, etc. But what's going to be the mean amount charged or the expected amount charged? So we're not going to have to do a lot of work here. Remember, the mean of x was 0.41, right? So knowing this, knowing what A is and knowing what B is, namely 300 and 500, we could quickly get the mean of y. So 300 times 0.41, remember that's 300 is the one that is multiplying our random variable, plus the fixed amount. Okay? Then question 7, I'll leave that to you for you to compute. Okay, that's simple enough math there. By the way, that's going to be in dollars. What is the standard deviation? So let's get the variance first, and then we'll take the square root of the amount charged. So that's y. So this could be a huge pain in the butt, except we use the previous results we had, and we know that this is going to be a squared times the variance of x. Perfect. So a is 300, so 300 squared. The variance of x, if you recall, was 0.5219, okay? And that is how you get the variance. If you want the standard deviation, take the square root, right? That will be whatever it is. I'll leave the math up to you. And that is how you get the mean and standard deviation or variance of a linear function of a random variable. And by the way, this goes for both continuous and for discrete, the results that we had on the previous slide. Okay? So, hope this was a helpful introduction to random variables. Recall the basic definition, basic concept, and then the specifics of discrete random variables versus continuous random variables, and finally some of the results that we learned from taking linear functions of random variables. Till next time, like, subscribe, and share, and have a great day.